All right, so today we are going to be finally talking about why are trigonometry functions called trigonometric functions. So in other words, we're going to be looking at these trigonometry functions, which we defined in terms of the unit circle, and we're going to talk about their relationship to right triangles. And in order to save a bit of time, I've already put up a unit circle on the board here that we can refer to. And you'll notice that inside of this unit circle, I put a right triangle with an angle theta. Now, you'll notice something about this right triangle. The hypotenuse, which remember the hypotenuse is the long side of a right triangle. So there's the base and the height of the right triangle, and then there's the hypotenuse. You'll notice here that because this triangle is inside of a unit circle and the hypotenuse is a radius for the unit circle, that means that this hypotenuse has to have a length of 1. And the other thing that we know about this is from the definitions that we gave for the trigonometry functions, the trigonometric functions, sine and cosine, we know that the coordinates of this point are going to be cosine theta and sine theta. Remember, that's literally just the definition of sine and cosine. This point is the terminal point for the angle theta, and the coordinates of the terminal point on the unit circle are defined to be cosine theta and sine of theta. Well, what that tells me about the dimensions of this triangle is the following. It tells me that this distance here, if I start over here and I look at what is the length of this base, the length of this base is actually the cosine of theta. And if I look over here, if I look at the length of the height of this triangle is actually sine theta. So this is very interesting. It tells us that if I have a unit triangle like this, or I should say a right triangle inscribed inside the circle like this with the hypotenuse being a radius, then the base is cosine theta and the height is sine theta. But what if we had a different triangle? What if the triangle doesn't have a hypotenuse of length 1? Because in general, we want to deal with triangles that have all kinds of dimensions possibly. Well, here's what we can do for that. And let me erase this and start drawing a new picture here. I'm going to start off with a right triangle whose hypotenuse does have a length of 1. And we will put an angle theta here. Now, the bottom of this triangle is going to have a length of cosine theta, and the height of this triangle is going to have a length of sine theta. And to see that, you can just think about putting a unit circle around this triangle, just like we did in the previous diagram. It's really the same idea there. So I'm just kind of drawing this with no circle so that we have a nice, neat picture with just a triangle. Now, suppose that I had another triangle with the same angles. So I want to think about another right triangle here that also has this angle theta down here. But it's also a right triangle. Now, you might remember from geometry, I don't know how many of you took geometry, but I think that most of you have. You might remember from geometry that if two triangles have two angles which are the same, then their third angle also has to be the same. So this angle up here has to be the same as this angle up here. And that means that these are similar triangles. Now, the thing about similar triangles is that the ratios of all of their lengths has to be the same. In other words, you look at the corresponding sides of these triangles, and their lengths all have to have the same ratio. So, let's suppose that I call this length here A, call this length here B, and we will call the length of this hypotenuse C. Well, then what this tells me is that the ratio of the large triangle's lengths to the small triangle's lengths is always going to be the same as the ratio of the big hypotenuse to the small hypotenuse. So that means that all the ratios are going to be C over 1, because we made this triangle to have a hypotenuse of length 1. So that means that C over 1 is going to be the same as the ratio of A to the cosine of theta. In other words, A divided by cosine theta, and it is also going to be the same as B divided by sine theta. Now, I do want to point something out here. This argument would also work if, instead of making the ABC triangle bigger, I could also have made it smaller. So I could have said, well, what if A only extends partway along this base? What if C only extends partway along this hypotenuse? I would get exactly the same equations. So I'm going to let you guys work that out for yourselves. Think about what would happen if you made a similar diagram, but where the new triangle with sides A, B, and C is smaller than the original triangle with a hypotenuse of 1. And you'll see, actually, you get exactly the same equations here. But the nice thing about this is that really the dimensions of this original triangle, we can kind of ignore the fact that that original triangle is there, and we can just think about the following conclusions from this set of equalities down here. We can say A is equal to C times the cosine of theta, and B is equal to C times the sine of theta. And this is going to be true in general for any right triangle. We are going to get these equations. There's a nice way of kind of remembering what is going on here for any right triangle. So here's what we can do. We can think of this as, instead of labeling a right triangle with A, B, and C, we have some angle in our right triangle here. I'm just going to call this the hypotenuse along here. Now, this side, which is touching the angle theta, I'm going to call this the adjacent side. And you can remember it's the adjacent side because it's literally adjacent to the angle that I'm thinking about. This side I'm going to call the opposite side. It is opposite to this angle theta, so opposite is a good name. We can remember it hopefully fairly easily. And if we think of the original labelings, I had originally labeled this side as A, this side as B, this side as C. So what these equations really tell me is that the adjacent side is equal to the hypotenuse times the cosine of theta, and the opposite side is equal to the hypotenuse times the sine of theta. Another way of thinking about this is that the cosine of theta is equal to the adjacent side divided by the hypotenuse, and the sine of theta is equal to the opposite side divided by the hypotenuse. That doesn't really look like an H. There we go. Hypotenuse. So this is actually another way to characterize sine and cosine. Instead of using the unit circle, you can actually characterize sine and cosine by the ratios of a right triangle like this. In fact, if you look in your textbook, they introduce this definition first, and then they show how this relates to the unit circle. The way that I've done it in these lectures is I've introduced the unit circle and then showed how it relates to these right triangles. The problem with introducing it in terms of right triangles is this. For a right triangle, this angle theta has to sit somewhere between 0 and a right angle. Now, a right angle in radians is pi over 2. A right angle in degrees would be 90 degrees. So The problem is that this definition only works for angles theta in the interval from 0 to pi over 2. And that's kind of a problem if you want to define this function everywhere. So that's why I like the unit circle definition as our kind of basic definition, and then we can see that these properties follow when we're talking about angles between 0 and pi over 2. If we use this as our basic definition, then we would have to say, okay, so how do we want to kind of extend this function beyond this domain? And then we can go to the unit circle and say, okay, well, it makes sense to kind of say we extend it using the unit circle, but I think it just makes things more complicated. Anyway, for the angles theta that are between 0 and a right angle, we can also think of this as 0 degrees to 90 degrees, if we want to think about it in degrees instead of radians. Then you can just use these definitions. And you remember, by the way, hopefully, that the tangent function is the sine function divided by the cosine function. So we can also say that tangent theta is sine theta over cosine theta, which, if I look at these ratios, take a minute and think about this, but what would I get if I took sine theta over cosine theta? All right, hopefully you guys figured that out, but if not, let me show you what you would get. You're going to have opposite over hypotenuse divided by adjacent over hypotenuse, and that means that these hypotenuses are going to cancel with each other, and we end up with tangent theta is equal to the opposite side divided by the adjacent side. So we can kind of add this as a third definition here. The tangent is opposite over adjacent. By the way, some people like to remember this definition using a little mnemonic. Now, I was not taught this when I learned this stuff, and so I don't usually think about this really, but this might help you guys out some. Some people remember the mnemonic SOHCAHTOA, which I guess sticks in people's minds for some reason. And the way that this works is sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. So it really is just a way of remembering these three relationships for triangles, kind of using this little nonsense word mnemonic that you have. If that doesn't help you, then feel free to completely ignore it and never think about it again. But if it does help you, then that's good, because you want to be able to remember this stuff. Finally, we can write down the last three trig functions in terms of these three relationships and the dimensions of one of these right triangles. So if you remember secant theta, this is 1 over cosine theta, so that's the reciprocal of cosine. Well, what's the reciprocal of cosine? If I write it in terms of the hypotenuse and the adjacent, it's just going to be hypotenuse divided by adjacent. If I want to do the cosecant, this is going to be the reciprocal of sine theta. Well, the reciprocal of opposite over hypotenuse is hypotenuse over opposite. And finally, we can do cotangent. That's going to be the reciprocal of tangent theta, and that is, of course, going to be the adjacent side divided by the opposite side. So you can really define all 6 trig functions in terms of these relationships of a right triangle. And in some ways, really the original way of thinking about trig functions really came from thinking about the relationships that hold for a right triangle. That's why these are called the trigonometric functions, because they are about the geometry of triangles, or trigonometry. Like I said, the problem with these definitions, and this holds for all 6 of these, is that this really only works for angles that are somewhere between an angle of 0 and a right angle. If you want to be more general than that, then you need to think about the unit circle. Now, one thing that this does make very nice for us, one thing that this makes it kind of easy to see, is an interesting relationship. You can actually show that this holds in general, not just for angles between 0 and pi over 2. But for these angles, it makes certain relationships very simple. So let me think about a right triangle here. And I'm going to call this angle is going to be theta. And this angle up here, we're going to call this, well, we're not going to call it really anything for the moment. I'm just going to write down what it is. This is a right angle, which is an angle of pi over 2. And this is an angle of theta. Now, for the moment, I'm just going to call this angle x. One thing we know about triangles, if you add together the 3 angles of a triangle, you have to get, in degrees, 180 degrees, or in radians, that would come out to be pi radians. So one thing we know is that theta plus pi over 2, that's this angle here plus the right angle, plus x, this is going to have to be equal to pi in radians. And that tells me that this angle x is equal to, if I subtract things over to the right-hand side, I'm going to get pi minus pi over 2 minus theta. That becomes pi over 2 minus theta. Now, what does that mean in terms of sines and cosines? Well, the sine of x, let's label these sides here. We have C, and we'll label this as A, and this is B. This tells me that the sine of x, which is going to be the opposite side for this angle x, divided by the hypotenuse C, this is going to be equal to A over C, but this is actually also equal to the cosine of theta. And what this implies, which we'll indicate with this little doubled arrow here symbol, what this implies is that the sine of pi over 2 minus theta is equal to the cosine of theta. Now, what if I wanted to do the cosine of this angle x? Well, this would be the ratio of the adjacent side to x, which would be b, divided by the hypotenuse. And what would that come out to be? Take a minute, think about this, see what you can work out. All right, so hopefully you paused for a moment and tried to think about this a bit. Well, how could I relate this back to the sine and cosine of theta? B is the opposite side here. So B over C is actually just the sine of theta. And this tells me that the cosine of pi over 2 minus theta is equal to the sine of theta. So this gives me 2 interesting relationships here between sine and cosine. And it's maybe not too surprising that we got these relationships. When we looked at the graphs of sine and cosine in the previous lecture, we kind of saw something very similar to this happening. We could kind of guess that this would be the case. If you go and you look in your book at the graphs of these functions, you will find that they look like they have this kind of symmetry. One graph is just the other graph kind of shifted a bit and reflected. And actually, the reflection doesn't really change anything, depending upon which way you're going. So I'm not going to go into detail about how this graph stuff plays into this, but if you look at it, you can kind of see, yeah, this is something that we would expect. Now, I do want to say, I only proved this for angles between theta and pi over 2. We did not show that this has to be true for general angles. However, it turns out that this is actually true for all angles. And I'm not going to show you the proof of that. You can prove that geometrically. It just gets more complicated because when we start dealing with angles in other parts of the unit circle, then what you have to start doing is you have to start making just some more complicated geometry arguments about it. And I don't think that it's really enlightening enough to bother going through here. So if you're interested, we can talk about that together at my online office hours or something, and I can send you more resources on that, but I'm not going to go through it here. So, how can we use this sort of thing? And by the way, if you are feeling like you want to take a little break, this would be a good place to pause, get up for a few minutes, get a snack or something, and then come back, because we're going to look now at a few applications of this sort of thing. So, applications to triangles and problems involving triangles. So one way that we can kind of use this sine and cosine sort of thing is, what if I give you a triangle, like let's say that I give you this, and I say, okay, I have a right triangle here, the hypotenuse is 5, it has an angle of theta, and then it has two sides that are unknown. And we know that sine of theta is equal to, let's say, 1/3. And we want to know what are the values for A and B. Well, the way that I can answer this question is I can say, okay, sine of theta is opposite over hypotenuse, which is B over 5. But B over 5, the sine of theta is also given to me as 1/3, so I can take this and I can set it equal to 1/3. And this allows me to solve for B. I multiply both sides here by 5, and I get B equals 5 over 3. Now, what about finding the side A? Well, at this point, I can do a few different things. But the one that I'm going to focus on here, first of all, is I'm just going to apply the Pythagorean theorem. And using the Pythagorean theorem, I see that a squared plus b squared equals 5 squared. But I actually know what b is here. So this means that a squared plus 5 over 3 squared is equal to 5 squared itself is 25. This is going to give me a squared plus 25 over 9 equals 25. And let's see, this is going to give me a squared is equal to 25 minus 25 over 9. And I'm running out of room here, but let's see. So 25, this would become 225 over 9 minus 25 over 9. Apologies for running so close to the end of the board. And so 225 over 9 minus 25 over 9, this is going to become a squared equals 200 divided by 9. And you know what? Let's just go back up to the top here so that I have a bit more room to write. So if I have a squared equals 200 over 9, then this is going to give me that a is equal to the square root of 200 divided by 3. And the square root of 200, this is going to be equal to 10 times the square root of 2, and it's all divided by 3. Okay, so again, sorry that I kind of had to do this in a weird way on the board, but this gives us the dimensions of this triangle. And these are the kinds of problems that you might need to work out a lot when you're dealing with such things as maybe you're working on setting up some kind of a building. You know, it's an architectural kind of problem, and you need to know, okay, what lengths should we cut our pieces of wood? You know, you're making some kind of a structure out of 2x4s or something. Well, how long should they be? Well, you need to use trigonometry in order to figure that out. Now, I guess if you're doing something relatively small, you could probably just measure everything and kind of guess. But if you're dealing with something larger or something that needs to be really precise, then you're going to have to use these kinds of trigonometry arguments. Now, sometimes these problems are going to be given to you in a slightly different way. So maybe instead of what we just had there, what if we did the following example? So here I have a right triangle, and I'm going to put my angle theta up here this time, and I'm going to say that I know that this side has a length of 3, and we will label these sides as, actually I'm going to call this B instead of A, so we're going to label these sides as B and C. And if the cosine of theta is equal to, let's say, 3/4, what are B and C? Now, take a few minutes here before you watch what I do and see if you can figure out the answer to this question. All right, so the way that we have to do this is similar to what we did before, but it is going to involve a slightly different kind of actual equations that we get, but the kind of reasoning is still the same. So what I know is that the cosine of theta, this is adjacent over hypotenuse. Well, what is the adjacent here? The adjacent side has a length of 3 because the angle theta is this angle up here, and so this is my adjacent side. So this is going to be 3 over c. But I'm also given that the cosine of theta is 3 over 4. So what I get is that 3 times 4/3 is equal to c, or c equals 4. So now I've actually found what is the hypotenuse of this triangle. And now that I have the hypotenuse of this triangle, I can go ahead and I can find this last side by just using the Pythagorean theorem. So I can say 3 squared plus b squared equals c squared, but I just found c, so I get that 9 plus b squared is equal to 4 squared. This means that 9 plus b squared equals 16. Let's see, so that gives me that b squared is equal to 16 minus 9, which should leave me with 7. And that tells me that b is equal to the square root of 7. So my answers here are going to be that c equals 4 and b equals the square root of 7. By the way, you'll notice that when I take the square root, normally we would think about the fact that there's two possibilities, right? I could get the plus or minus of the square root. And in this case, I just took the positive. Can you think of a reason why that would be? Well, the reason why that is because these are lengths of sides of a triangle. And can a length be negative? Well, the answer is no, not really. Lengths have to be bigger than or equal to 0. You could have a length of 0 because you could have two things that are literally at the same point. But what you can't have is a negative length. our coordinate axes, those can have negatives on them because that's just talking about relative positions. But the actual literal physical length of something is going to be a positive number, or 0. I shouldn't say it's a positive number. It has to be bigger than or equal to 0. So positive or 0. All right, let's take a look at another example of these triangle type problems. So let us suppose that a tree has a height of 100 feet. And we calculate that the angle from our position to the top, and let's call this the angle theta. So we'll say the angle theta from our position to the top of the tree has tangent of theta equals 10/3. And we want to know how far are we from the base of the tree. Well, let's make a little diagram here just to kind of illustrate what's going on and see how this all relates to our triangles. If I have some tree here, we'll think of this as like a pine tree or something because I can't draw complicated trees. This tree we can think of as having a height of 100 feet. And we're standing somewhere over here. And we're looking up here. And, sorry, that is a terrible ground thing. So this is a right triangle. And this angle here, theta, has a tangent of 100 feet. So let's call this bottom side A. And we don't even really need to think about the hypotenuse in this case. So I'm not going to end up labeling it. What I know is that the tangent of theta is the opposite side over the adjacent side. And because this angle theta is down here, this side, which is actually the height of the tree, is the opposite. And this side down here that I've labeled A is the adjacent. So this is really just opposite over adjacent. But this is also given to me as 10/3. So what is A going to come out to be? Well, this means that 100 equals 10/3 times A, and that means that 100 times 3/10 is equal to A, so that gives me that A is equal to 30. And so, because we're working in feet, I know that this distance is in feet, so my final answer is that we are going to be 30 feet away from the base of the tree. Now, another type of problem that you could ask with these triangles is maybe I give you the lengths of some of the sides and then I ask you to find the sines or the cosines or some other kind of thing. So to give you an example of this, suppose that I tell you, here's a triangle and this side has a length of 2 and the hypotenuse has a length of 5. And here's my angle theta, and we'll say this is a right triangle. And I ask you, what is cosine theta? Well, we can figure this out. And there are a couple of different ways of thinking about this. But the way that I'm going to do this is I'm going to say, okay, let me call this base A. Now, what I know is that cosine theta is the adjacent over hypotenuse. And the adjacent over hypotenuse is A over 5. So what I need to know is what is the length of this side A? Can anybody think of a way that you can do that? So take a moment and think about, how could I find what this side is with the information that's given to me? So the answer here is we use the Pythagorean theorem. We know that a squared plus 2 squared equals 5 squared. That gives me a squared plus 4 equals 25, and that gives me a squared equals 21. So a is the square root of 21. Remembering that we can take the positive root here because we don't want to deal with negative lengths. Okay, well, that gives me a. The cosine of theta is a over 5, so this becomes the square root of 21 over 5. Okay, that doesn't look like a 21. Let's rewrite that as something that's legible, sort of. There we go. Square root of 21 over 5. Done. We can do this with literally any of our trig functions, in fact. So maybe what I give you is this. I tell you, okay, here is your triangle. Here's your angle theta. And maybe I give you that this side has a length of 6 and this side has a length of 4. And I ask you, what is cotangent of theta? Well, the thing that we want to remember is that cotangent theta is equal to 1 over tangent theta. It's the reciprocal of tangent. And what is tangent? Well, tangent is opposite over adjacent. So the reciprocal of opposite over adjacent would be the adjacent side over the opposite side. So let's call this side here A, the adjacent side. So this means that the cotangent of theta is going to be A over 4. Well, now I just need to figure out what is A. And I can do that by using the Pythagorean theorem again. So I'm going to get A squared plus 4 squared equals 6 squared. That's A squared plus 16 equals 36. And that gives me A squared equals 20. And that is going to give me that A is the square root of 20, which is going to simplify. Let's see, this is 4 times 5, so this is 2 times the square root of 5. So we get A over 4 is 2 times the square root of 5 over 4. And the 2 over 4, that can simplify, and this leaves me with simply square root of 5 divided by 2. So let's kind of give a quick summary of what do you do with all of these things. Well, when you're dealing with these kinds of problems, when you're trying to fill in the extra information, there's a lot to remember in some ways, but you do get used to it. And once you're used to it, it's not really that bad because the relationships are always the same. You just have to remember the relationships between the different trig functions. And this is where that SOHCAHTOA acronym or mnemonic might actually help you guys quite a bit in remembering those relationships. And then you ask yourself, what information do I know? And the third ingredient here, the really important third ingredient, is going to be the Pythagorean theorem, because often you know more than is given to you in the problem. Like, you'll be given some information in the problem, but actually from that information plus the Pythagorean theorem, you know more than I explicitly told you. Like in this case, in this problem, we actually know what A is because of the Pythagorean theorem without having to mess around with any trig functions. So in general, ask yourself, what can I do with the Pythagorean theorem to give myself more information if I need more information about these problems? Now, I'm also going to recommend that you guys watch some of the examples that are available in the video help on my math lab just to see some extra examples that are worked out. But really, this is the kind of thing that you need to practice these problems. So, I tell you guys all the time, mathematics is not a spectator sport. It's important to practice. And I think as you guys practice these, you will hopefully, you start to kind of pick up and these things sort of become something that you're more used to. When you start doing something new, it seems difficult at first. But eventually you start to kind of internalize it and your mind starts to recognize the patterns and kind of, you get used to it. If you're playing a sport, when you first start playing the sport, you're constantly thinking oh my gosh, what do I do? What do I do? What do I do? Well, after a while, you just look at the situation and you immediately know what to do because you've done it so much that you're used to it. And that's kind of what you need to do with these kinds of problems too. You just need to get used to doing them, you practice them a bunch, and eventually you start to say, oh yeah, these patterns, they make sense to me now. I see it, I see the pattern, and I do the problem. But you really only get that with practice. All right, so we will come back to talking more about trigonometric functions, and what you can do with them. But for now, I'm going to end this here, and I will see you guys later.